recording this. That's it. It's recorded. And then I see the red dot. And I will share my screen so everybody can see. So let's go to our next topic, Cohen's D. I tried to catch up this time, so di kay ko magdaghag chika-chika. Kay para mahuman yun na to ning di na dahin ko mabahin. All right, so let's start with Cohen's D. So Cohen's D, I sort of like created a website. That's my favorite website for Cohen's D is this one. It's from the R Psychologist. It's quite interactive. So it's rpsychologist.com. So Cohen's D is an effect size type of statistics. It estimates not just your statistical significance, but it goes above and beyond the statistical significant value of 0.05 and looked into how big is the effect or the effect of your intervention to the dependent variable or the outcome. This is very immensely popular, as you can see here, but its interpretation needs to be treated with some caution because even the developer of this statistics already said on his publication in 1977 that there are many dangers in the interpretation of the Cohen's D. After all, these are all probabilistic. So this is the general guidelines, is that if your Cohen's D is 0.2, you have a small effect. And most of us in social sciences or nursing sciences, when we develop intervention, our aim is always for a medium-sized effect of our intervention. And then we will be so happy if we will get a large effect, which is about 0.8. So what does that mean when we have those Cohen's D? So this is the one that has interactive. So if we say if it's 0.2, you can see here that this interactive model really moves, and it provides you the common language or explanation if your Cohen's D is 0.2 or 0.3 for this example. With a Cohen's D of 0.3, 62% of the treatment group will be above the mean of the control group, and 88% of the two groups will overlap. And what happens when you move this to 0.5, because that's our goal. Let's say 0.6, because that's our goal. We want to have a medium size effect of our intervention. So in my example would be the one that I presented at the American Society of Hematology in San Diego just this past December. And we will demonstrate what Cohen's D is all about with an actual data set. So we developed this educational intervention. It's a 1-hour video that the physicians and nurses took this 1-hour intervention that talks about shared decision-making. And we give them 3 questions, a pre-test and a post-test questions. And we determined their mean score in the pre-test and post-test, and we added a Cohen's D to look at what is the effect size of that 1-hour video education that we did on shared decision making. So we developed the shared decision making based on the key concepts by Charles Gaffney and Whelan, and based on the studies that I've done also on shared decision making. So the interpretation for a 0.6 is that with a Cohen's D of 0.6, 73% of the treatment group will be above the mean of the control group, and 76% of the two groups will overlap. So there is this concept that there is overlap, and there is the probability of how many of the treatment group will be above the mean of the control group. So for those who did not have the intervention. So the highest one that we aim for, that we say is a large effect size, is 0.8. And this is the interpretation of 0.8 right there. And this is already considered where you have 79% of the group of the treatment group will be above the mean of the control group. There's a caution there because as you move this effect size to 2.6, you will see that that's a very huge effect size. Well, it says here that 100% of the treatment group will be above the mean of the group and 19% of the two groups will overlap. So that's where the caution comes in because of this overlap that was built into the calculation of the Cohen's, the theoretical concepts of Cohen's d. So this is the formula of Cohen's d, is that Cohen's d is equal to the mean of your control, the mean of your treatment group, and minus the mean of your control group, and then divided by the standard deviation. So this is actually very simple formula, but there is a big but here, because you cannot just use this formula from your regular statistics. You have to have a paired t-statistics, and you need to get the means from the paired statistics in order to use Cohen's d. So that's a requirement because there is you have your pre and post, and so before they got the intervention and after they did not get the before they get the intervention and then after they get the intervention. So Cohen's d, instead of just doing, is there a statistically significant difference in the pre and post test mean score of their knowledge and your education? And you can say, yeah, there's a statistical significance. The next question is, how big is the effect? And that's Cohen's d is an additional statistics that is very popular right now because it gives you an estimate of the effect size of your intervention. But it requires the mean from a paired t-statistics. Without the paired t-statistics, you cannot apply Cohen's d because the math is very complex. It's right here. We're not gonna cover that, but it accounts for differences in the means before the intervention, after the intervention, and then it looks at the standard and you divided it by the standard deviation. So let's take a look at an example of what I have done. So right here is my clinical care options where we had three questions that we looked. What was the pre-test score of the participants in our study when it comes to selecting the correct answer about what should be the right answer once you already know what shared decision making is all about? And that means that shared decision making, there has to be an exchange of information, that the patient is the focus of the decision making process, and that the patient had the time for deliberation, and that you accounted for patient's preferences and personal evaluation of the treatment options. So we introduced this intervention, this educational video intervention, and then we give them a pre-test and we give the scenario and we look at those who got correct and incorrect answer, and we can say that the incorrect is 0 and the correct is 1. So we had a binary yes, no kind of data. And then we also look at management of side effects, because this is a program on multiple myeloma. So aside from the shared decision making, we also look at their scores on the correct way of managing the side effects, whether the correct answer, what was their score pre-intervention of the video, and then what was their main score after the video education intervention. So we plug that in, is you need to do your analyze and you compare the means. We already checked the distribution. This is parametric, it's mean, it's knowledge, and just trust me when I say that it's a normally distributed data that it meets the parametric assumptions of all the t-tests. So we go to the paired t-test, and I plug in here the pre-test and the post-test score, the 3 questions that we ask. And if you click options, it's 95% confidence interval. And then we press OK. But what I'd like to show to you that when you have your raw data, be careful because right here, this is one of my students. And if you just do pre-test and post-test, but you don't actually tell the computer to compute, which will create another variable for you, is that it will compare the pre-test of every single variable that you have. So you actually need to use this function transform. You compute the variable. So I already calculated, just to save time, I did the pre. But what about if we also need to do the post, right? So these are the posts. I know that PV is post, pre is pre-vid, this is post-video, this is pre-video. So you actually need to tell the computer, SPSS, to get the means of the 6 variables. Or else the computer will give you individual pre and post-test differences for your pre-test 1 and pre-test 2, pre-test 1 and post-test 2, previous 2 and post-test 2. You don't want that. You really have to get the average of all your entire questionnaire. So we're going to name this as mean post-test. And when you create a variable, there's no space. And then the label, you can put now whatever label you want, mean score post-tests. And that's numeric because SPSS only knows number. So, and then now, because you want to get the mean, I know that all of my values were just named PB 1, 2, 3. So after PB, I will add plus. My numeric expression is to get the mean. It's just to put plus. And I understand the way how I name my variable. I know that it's after the number is where my variable name ends. So now I double check. PB1 has a plus, PB2 has a plus, PB3 has a plus, PB4 has a plus, PB5 has a plus. If you are really a real statistician, there's a shortcut for syntax for this, but that's, if you take SPSS class, there's a lot of shortcut. But now this is for you as a PhD, and we really are not bombarded with 20 million data sets every day as our day-to-day job. I think that you can do manual like this. And then we press OK. And look what happened. It created another variable. There's now your mean for the post-test. So with this one, I can actually say now that analyze and then compare the means, and this is a paired t-test. And then I can use now my pre and then my post, and then make sure that this is already the default. And I press OK. And there you go. You got your paired t statistics, which is statistically significant. There were 23 subjects in the study, so the degree of freedom is 22. And the t statistics value is minus 4.989. And if you have your t statistics table right now with you, you go at the back of any statistics book, there's always the t table. You're going to find that minus 4.989 will have a significance value of 0.00000. So we know it's highly statistically significant. The other thing here is that when you look at the mean, When there is a negative minus 5.5, that's always a good indication that your intervention really worked, because this is what is the mean score in the pre-test and what is minus the mean score of the post-test. So if it's negative, it's telling you that it improved. That's why it's negative. When it's positive, it's really bad because they actually have a higher score before your intervention, and then when they got the intervention, your video education, they got so confused that their answers became wrong. So you'd like to see this to be minus, but we're not done here. So this is the foundation of Cohen's d. Cohen's d said that the formula is Cohen's d, which was a sign, I think was sigma, is equal to the mean divided by the standard deviation. So, but it needs to come from your paired t-tests. So what you can do here in our example for my clinical care options for my abstract, so this is now the t-test output, and those who got the correct answer pre the video CME minus the correct answer post video CME, and we got a minus 0.45. So we're very happy. We know that that our intervention made a difference. Same thing with, will they consider the data and what was their correct answer, and then will they consider the data with the shared decision making after the post video education intervention, and we get the minus 0.38 mean again. But these are the mean from the paired t statistics. And then for our third question is, are they able to give the correct answer in explaining the side effects pre-test? What was this mean score? And minus the correct answer for managing the side effects post-test. And again, we had a negative mean score in the paired t-test, which shows that our intervention worked. So if we just simply plug in the number to get the Cohen's d, mean divided by the standard deviation from the paired t-test statistics. So the first one would be minus 0.45. Calculator. I'm only going to show only one calculation because it's not that complicated. So minus 0.45 divided by the standard deviation of 0.59321. And that's the 0.758. And let's see. The number did not match up, so I'm gonna look 0.3. Maybe I did not plug in all the numbers. 0.49. There you go, 0.77, which is 0.78. So I think that that's just a function where if you plug in only the first two digit, 0.43 divided by 0.504, and that's 0.85. So these are all the effect size that we get. So we're very pleased that our Cohen's d is definitely 0.5 or higher. So when we reported our abstract to the American Society of Hematology, this is how we reported it then. and it shows you that what's the percentage and our effect size calculation. And we include the p-values. And this was accepted, and I presented this at the American Society of Hematology. So it's important that we not simply get the statistical significance of our intervention, that modern statistical guidelines are now looking for the effect size of your intervention. So that's what Cohen's D is all about. Any questions? It's not very difficult, I would say. This is probably one of the easiest one because you just plug in the numbers from your paired t statistics. It's just mean divided by the standard deviation from the paired t statistics summary table output from SPSS. SPSS does not produce a Cohen's D. So you still have to manually do it. Don't know why. It's been published since 1977. Sometimes politics, maybe. The people from SPS said, nah, we're not going to put that in one of our functions. But the other software, Stata, will already do the Cohen's D. It's already built in their different functionalities. But for SPSS, you have to just get the paired t-test, and then you manually plug in the mean divided by the standard deviation from the paired t-test statistics output. All right, let's do this. And if we are cut off, it's 9:22, we will just immediately move to the next time slot. And then we're going to cover exploratory factor analysis. Yay, we're really good tonight. All right, so what is exploratory factor analysis? What is a factor analysis? Well, it's a statistical tool for analyzing large number of variables. So in my video, we have 22 variables there, and we want to see if there are identifiable groups of variables referred to as factors. So when I developed the shared decision-making tool for shared decision-making for nurses, SDMS scale -N, so shared decision-making scale for nurses, I already have theories in my mind that my variables or the items in my scale will group together. And I sort of theoretically label them as knowledge, attitudes, and skills, because those are the key concepts of competency. And I use the model of shared decision making, the iceberg model of competency, which shows that the very visible, measurable level for competency is the knowledge and skills. And then it's harder to measure the deeper part of the iceberg, which is 75% lower, are the attitudes, the personality, the motive, the dreams and aspirations. All of that are the driver for competence. So when I develop my tool, theoretically, I already make some conceptual grouping of the different variables into factors. And for now, I created 3 factors. But what factor analysis will do is when you administer this tool, once you already put this, that's what they call the rubber hits the road, so to speak. They said that, okay, the work starts now. Once I will have my data, I'm planning to start, I'm going live with using the Qualtrics online survey, and we're sending it to over 800 nurses, oncology nurses. And we're hoping we're going to get 240 responses because for each variable or item, there has to be 10. And we multiply it, we have a total of 22 in our bank. It's called the item banks when you develop a tool. And if you assume that there's a 5%, 5% the sample will have only half of the tool will be completed, then it's good to overcalculate or oversize your sample size, because you always have to account for potential missing values. And you don't want, when you develop your tool in the beginning, you really don't want to have a smaller sample size than what's required. So this is what factor analysis is all about. They're going to look at the shared variance, and they make the factor analysis will make conceptual sense to group those variables into factors because of shared variance. Mathematically, factor analysis is a linear combination of variables. So that's why they hug each other, because they have a linear combination of variables. And it's often used in the construction of scales, as what I have just shared to you, my shared decision-making scale, to measure latent variables and construct, which means that what are really the deeper relationships of the different variables, and that's what we call latent variables and constructs. Latent constructs are very complex ideas that are not directly measurable or observable, and they are measured by combination of observed variables. So factor analysis, exploratory factor analysis, will show you which of those items group together, and if they don't hold your theoretical assumption that these are knowledge, that these are attitude, and that these are skills, then you need to analyze it again. It's like, boy, what is this? Why are they grouping together? So how are my items worded? And why is it that they have a linear combination to each other, and why is it that they have a shared variance? So you can theorize from the very beginning, but once you have your data, you need to be objective. The data is speaking to you, and you need to interpret what is the meaning now of these items that group together. But in the beginning, you are very much guided. So when I developed my tool, all of the items were deductively developed. The wordings were derived, so they're deduced from the theories. So I have 3 publications in shared decision making. I've done studies, I've done literature review, and I look at the key operational definition by the authors of the shared decision-making model, which is who are Charles Gaffney and Whelan. And so I'm guided by theory to develop my measure, but I don't know how that theory will hold when I will get my data. You aim for the best and aim for the moon and the stars. And if you fall, maybe you fall in the sky. It's not so bad. So always aim very high. You have that very good idea of what is it that you're really trying to measure, and what are the construct that you're trying to plug in those items. But the latent construct, latent variables are the one that we don't know. How those variables that you originally proposed as groupings, how are they going to behave later on? So those are what we call latent construct. So example is to measure the latent construct of self-management of diabetes. You can really put a lot of things there, but then later on when you have your questionnaire and then they group those items in your questionnaire together, then it looks like that's my 10-minute warning. It looks like, you know, the latent construct for self-management of diabetes is all about checking blood sugar, adhering to diet, and using insulin. And that's what self-management of diabetes is all about. So these are the items that had a linear combination, and then they group themselves together. So that's what we call latent construct. The variable used to measure the latent construct of self-management would be constructed as a scale using a combination of the answers to the individual questions, and you need to pay attention to what would be these different items that will group together. The types of factor analysis are exploratory factor analysis, and you also have confirmatory factor analysis. So exploratory is to reduce the set of data. So I have 22 items. Perhaps my exploratory factor analysis will reveal that I will only have 18 out of the 22, and that maybe 5 items in the first subscale, and then maybe 6 in the other subscales, and then maybe 7 in the other subscales, a total of 18 in my scale. But then I have originally in my bank 22, but we don't know why those 4 other items in my item bank did not pan out. And that's why you need to keep thinking, and you need to keep on improving your tool. So item development is just the first step. You have to refine your item, and then during exploratory factor analysis, it tells you if I delete this, what would happen to my Cronbach alpha. Confirmatory factor analysis is already testing the hypothesis of the structures of the theory and all the concepts, all the variables that is in that theory. This may follow an exploratory factor analysis or may come directly from the theory. This slide is all about exploratory factor analysis. We're going to skip the question and answer part. It's exploratory factor analysis is a group of items that belong together because they measure a similar underlying construct. So the items group together, they have high correlation with each other of the same factor and not so high correlation with items of different factors. That's the key word. There has to be some variance, because if there's no variance, then you will not be able to see what's the differences in your construct in a theory. In a bigger picture, what are the different construct or concepts in your theory? So in my theory is the theory of competency. My constructs are knowledge, attitudes, and skills. I don't know if that will hold together. And I have to look at the items that did not have a linear combination and try to analyze, what could this be? Why are they, why are the respondents and participants? That's the data. That's the actual data. That's the representation of your theory, is the data. Factor analysis helps provide validity evidence concerning the internal structure of the instrument. It's followed by a computation of Cronbach's alpha coefficient, which measures your internal consistency of the set items. And then the type of data is that there's no dependent or independent variable. See, that's factor analysis. No dependent and no independent. You let everything loose, and you look at your exploratory factor analysis and how many will group together. And there is an eigenvalue that guides you. And then the scree plot will tell you immediately, visually, how many are considered as your factor. These are the assumptions: that the variables should be approximately normally distributed. All variables must be reliably measured. At least 10 subjects for each variable. And so I've said to my case that in my research study on shared decision-making scale, that I had 22 items. So I have to have a minimum of 220. I calculated a 5% respondents may not complete the survey. And so that's roughly more than 10. And so if I will have 240 and I can throw away 10 to 15 because they're not complete. They're not 100% complete, filled, or did not completely answer all the questions in my scale, then I can throw away those incompletes. The incompletes needs to be really not included in factor analysis because they're, especially when you start developing a new tool, you cannot afford those things. So I think I have another 4 minutes to go. And then this is the procedure for factor analysis. You state the hypothesis, and then you define the significance level. You collect the data of interest, and then make sure the data meet all the necessary assumptions. Examine all the bivariate relationships. So there's item to item correlations, item to total scale correlations as well. There's many things that you need to look at. Factor analysis is one of the most complex analytic procedure that you will go through as a PhD, because you imagine you're trying to develop a hypothesis or test a hypothesis. You conduct your factor analysis and then name and interpret the factors from the rotated factor loading matrix. So you need to put your critical thinking hat once you have your data and try to really ask the question, what is this latent construct that the data is shouting at me? It's like, you need to be Rodin, the deep thinker, that you have to really look, okay, why is it that my item 1, 4, 18, and 22 are grouping together? They're not supposed to be this way. My theory says my item 1 to 7 are knowledge, my item 8 to 17 are attitudes, and my item number 19 to 22 are skills. So how come that item number 1, item number 11, item number 23, item number 22, and item number 18 are grouped together? That's where it gets very complicated, because now it's no longer following your theoretical assumption. But that's what the data is telling you, that you have 220 respondents who says, these are commonalities. These are linear combinations. And so I can't wait to have my data, actually. All right, so it's 9:38, maybe another 2 more minutes. The data meets the assumption. The variables are all ordinal measurement scales. So just like our Likert type scale are ordinal. The variables are roughly normally distributed, and each variable is correlated with at least some of the other variables, so what you call the item to item correlations. And again, 10 cases for each variable. The interpretation, the first one is the Kaiser-Meyer-Olkin, or the KMO measure. It's based on the principle that if variables share common factors, then partial correlations between pairs of variables should be small when the effects of other variables are controlled. So that's why the matrix will show you that there's item to item correlation, and then there's item to total scale correlations. And then based on linear combination, it tells you which of this 22, in my case, 22 grouped together, and how many factors or latent constructs have been developed after you get your data. All right, why don't we take a 5 minutes, because we are now interpreting the result. So now it's 39 or 9:40 in my time. Let's catch up at 9:45, because I don't want to stop. This is the most important part, is I'm going to start with the factor analysis interpretation. All right, see you in 5 minutes.